Hello everybody, my name is María Fernanda Gazulla and I am from the Instituto de Tecnología, Cerámica, Castellón, Spain. My talk is on the determination of toxic metals in geological materials used in the food industry by ICP-OES. Some geological materials, such as kaolins, clays, nitrates, carbonates, are used in the food industry, either as additives or technological contributors, where determined heavy elements present at trace level must be thoroughly controlled with regard to food security. Clays are used as fining agents in oil and animal fat treatments to eliminate impurities such as gums, phosphatides, trace metals, or fatty acids present in oils and fats, which can oxidize the products and can therefore reduce their shelf life. Fining clays remove these substances and also other compounds that color the food stuff, chlorophyll, xanthophyll, and carotene. Fining and blanching is a process in which an adsorbent substance is introduced in a liquid with the aim of removing proteins and organic colloids that could precipitate or cloud the liquid when it is settled. Due to the small size of these proteins and colloids, they cannot be eliminated using a conventional filtration process. So, the properties that a geological material should present to be used as a processing aid are high specific surface area, cation exchange capability, and swelling degree. Calcium carbonate are used as an additive because it's very useful for the digestibility of the food and also is used in bakery, in drinks and cereals, canned fruits, and so on. Potassium nitrate is used to prevent meat industry, cheese, etc. from bacteria and fungi. Food contamination from heavy metals such as arsenic, cadmium, chromium, lead, nickel, and mercury must be strictly controlled because cadmium can generate from anemia to cancer depending on the exposure time. Arsenic can cause lesions in skin as well as in the nervous system and liver and can be lethal in high exposures. Many diseases are related to lead absorption, being sharpened in children. Chronic poisoning of mercury results in damages to the central nervous system. Chromium can cause skin rash to respiratory problems or lung cancer. Nickel effect over human health is mainly related to respiratory problems from asthma to lung, nose, or larynx cancer. So, the regulation for the addition of a substance in food imposes strict controls to assure its harmlessness in the suitable dose for its use. So, the aim of this study is the development of a measurement methodology by ICP-OES in order to reach the quantification limits required in the food regulation for these materials with a minimum time as the method could be used as a control method and that the new methodology be environmentally friendly. Several samples from different suppliers of geological raw materials were selected to be able to carry out the present study. Exactly 2 clays and a cepiolite apart from the corresponding certified reference materials used. In order to have enough reference materials to carry out the calibration and the validation of the new method, the following organizations were consulted: BAM from Germany, BAS from England, Cadmium Materials from Canada, IRMMM from Belgium, NIST from USA, CGL from Mongolia, IAG from England, GBW from China, and SBAS from South Africa. From this group of reference materials producers, we have chosen a total of 10 certified reference materials. And these materials were used to validate each element from lead to arsenic, working in a big range from few ppms to high concentration, in order to have all the range of work studied. The development of the methodology of trace heavy metals was undertaken in 2 steps, completely different. The first one is the sample preparation process, and the second step is to optimize the measurement conditions. The optimization of the sample preparation was carried out studying the following variables: the sample weight, the type and mixture of acid, the addition of fluorhydric acid, the volume total of acid, the digestion temperature, and the digestion time. And the optimization of the measurement conditions was carried out changing the plasma power, the plasma flow, the nebulizer flow, and the peristaltic pump speed. To optimize the sample preparation method, different experiments were carried out by changing each variable between the ranges shown in the table. 35 reference materials were used to perform the optimization to ensure the accuracy of the sample preparation method developed. Traditional digestion methods recommended the use of hydrofluoridic acid in order to obtain a complete digestion of the geological samples. But the use of this acid brings about serious issues, as it attacks the glass materials and it is extremely harmful. So it is not recommended its use, at least there is not any other solution. After many experiments, it was noticed that the optimum extraction for the determination of arsenic, cadmium, and mercury is different from lead, chromium, and nickel. Finally, 2 digestion methods were developed. One for arsenic, cadmium, and mercury, when 1 gram of sample and 12 milliliters of inverse aqua regia were used to digest. And another method for lead, chromium, and nickel, taking 0.2 grams of sample digested with 8 milliliters of aqua regia plus 1 milliliter of fluorhydric acid. A set of conditions were optimized for each group of elements to obtain the best rate signal background and lower the uncertainty of the measurement. Mercury had to be measured with different conditions due to its high volatility. Plasma powder and plasma flow were optimized in order to get low plasma temperature to avoid loss of signal. Nebulizer gas flow and peristaltic pump rate were increased in order to get better sensitivity. On the other hand, since hydrofluoric acid was used to determine chromium, nickel, and lead, different measurement conditions were optimized in the ICP-OES as an inert sample introduction sample was used. Finally, we obtained optimum conditions without the need to use hydride generation, and we were succeed analyzing 1 ppm of mercury. The detection and quantification limits were calculated in accordance with the ICP-OES guidelines. The precision and accuracy were determined by the determination of the uncertainty calculated from the expression taking into account the uncertainty of the certified value, the uncertainty of the measurement of the CRM, and the uncertainty of the measurement of the sample. In order to compare the result obtained either with the certified value of the CRM or with values obtained by an independent technique, the difference between both was compared with the related uncertainty. And in that way, we can analyze the goodness of the method developed. In this table, it is shown the 8 materials, analyzed, and we can see that the results are quite accurate. They're quite similar. There is not a significant difference between the certified and the experimental value. We use, as you can see in the table, 2 methods, one for the arsenic, cadmium, and mercury, digested by method 1, and chromium, nickel, and lead, digested by method 2. Good agreement between the certified values and the results by the new method for the analyzed reference materials, since the difference between the values is smaller than the related uncertainty in all the elements analyzed, thus validate the methodology. In this table, it is shown the comparison between the results obtained by ICP-OES and wavelength dispersion X-ray fluorescence into clays and cepiolite. As you can see, there are not significant differences between the values obtained. The main difference between the two techniques is the quantification limit, being lower in ICP-OES method. To summarize, we can say that we have reached the 3 objectives of this research. The first one is to obtain a quantification limit enough low to be used as a control method for analyzing heavy metals in materials who have to be in contact with food. The second objective was to decrease the time of analysis to a minimum. And finally, with the new methods of preparation of the sample, we obtain a sum up time between preparation measurement less than 2 hours for a sample. And the third objective was to develop an environmentally friendly method, and we use minimum quantity of acids and no high temperature. So we finally reached the 3 objectives. We have a rapid and reliable method to be used as a control method. To conclude, we can say that a new robust and fast quality control method has been developed to ensure the absence of heavy metals in food that are hazardous for humans. The method, based on a new microwave technology for analyte extractions, permits the determination of all the heavy metals studied in a relatively short time, less than 2 hours. A sample preparation method for ICP-OES was optimized, depending on the group of elements to be measured. One for arsenic, cadmium, and mercury, and another for chromium, nickel, and lead. ICP-OES method is suitable as long as the requirements are 1 ppm for all the elements chosen. And finally, the methodology developed is environmentally friendly as it decreases the amount of acids needed to carry out the sample preparation, and there is no need to use digestion processes at high temperatures. And many thanks to my lab colleagues who are responsible for the good results achieved. And the Generalitat Valenciana, because through the Valencian Institute of Business and Competitiveness support this research. And thanks you all for your kind attention.